So installing VAV controls is a great idea from controlling to a demand-based operation and saving energy when the hoods aren't in use. But if you go too low or they don't control properly, then we can create safety issues that can come back and eliminate any of the value of the energy savings. If the hood's not functioning properly and somebody gets exposed or there's an explosion, the energy savings are irrelevant at that point. We need to be safe first. So monitors are really important. They can measure face velocity, they can measure flow, they can report pressurization. Well, this particular facility felt like there wasn't enough consistency and confidence in the method of measuring the face velocity of flow. So they put a pinwheel in. And the pinwheel would spin when the sash was open. Okay, I thought that was kind of creative. An interesting way to confirm flow, but I may not recommend it as a reliable means. And of course, the tissue paper as a secondary means of confirming velocity. Again, it's a means to check whether you got flow through the hood, but it's not very meaningful in terms of a monitoring system. So let's use the right type of monitors. And how do they get calibrated? What are they reporting is another factor. The monitor on the left is reporting velocity when the sash is closed. And you can see it says 260 feet per minute. On the right, it says 49 feet per minute with the sash open. Then there's some lights. The lights down below in the 260, it says safe, green. But over here at 49, it's showing yellow. Shouldn't it be an alarm? What dictates these set points of acceptability? Whose job is it to say this hood should operate between a range of 90 to 110 when the sash is open or some other range? And how low do you go and what does it report when the sash is closed? So these have to be discussed before you start testing the hood so that you can accurately calibrate it and then determine the set points for alarming and indicating the user when it's not functioning properly. Very important, and we see problems all the time in these different methods of reporting. Another factor is the response. If the sash is full open, we're expecting, let's say, 100 feet per minute. Well, what happens if we close the sash 50%? Or we go down to 25%? Is it modulating the flow in a linear fashion? This is called the VAV control test, and it's a test of its linearity. From 25% to 50% to 100%, it's modulating the flow. But we don't know what the flow is when the sash is closed. We can only say, across this range, it's modulating the flow as we expect it to, and we can measure that with a velocity probe. So in this case, it's good. We're saying it's got the linearity of control is acceptable, and we have to have some ranges around what it means to be acceptable. Essentially, I say it's plus or minus 10%. That's what we're looking for in terms of control. But when the sash is closed, we can't measure face velocity. So back in the 90s, a fellow named Dale Hitchings, he said, you know, if we measured the velocity in the slot of the baffle, this velocity through this bottom slot would be directly proportional to flow through the hood. So we came up with two methods. We said, one, if you're able to measure the flow directly from the flow sensor, terrific. You can report that flow. But if you can't get any access to it, maybe just take the velocity probe, put it in the slot, and now we can measure that velocity when the sash is in the closed position and verify that the flow is modulating between sash closed and sash open. So we start taking our readings, sash is closed, we open the sash, we expect there to be some delay before it starts opening, and then it increases the flow, and we might get some overshoot and undershoot, and eventually it gets stability. The time from when we open the sash to get to 90% of the movement of the flow, that is our speed of response, and it should be less than 5 seconds. And then the stability of flow when the sash is open should be less than 20% variation. So let's look at an example. We're going to measure the velocity in the plenum in the slot here, and I'm going to speed this up so that you don't have to sit through the 5 minutes. All right, so we're moving along, and at 30 seconds, I'm going to come in and open the sash, and we're going to see the flow increase, right? And so now the flow is increased, and then we're going to wait for 60 seconds, and we're going to come in here, and we're going to close the sash, and we see the flow going back down. And we're going to go through 3 cycles of that, opening and closing the sash, and we're going to look to see, is the values the same at sash open and closed, and is there any variations that would indicate a problem in the control? All right, so that tells us that this system is working properly. All right, so let's look at some of the data. So again, we're measuring the slot velocity. If the flow is significant, high enough when the sash is closed, it's repeatable in that we go through 3 cycles, sash open and sash closed, and this tells us that the flow is being appropriately controlled. However, the one on the bottom you can see is overshooting and undershooting, and it's not in control, it's hunting and seeking, and that's going to affect containment. Let's look at that another way. So we want to have adequate minimum flow in accordance with our specifications to prevent the unsafe accumulation of the concentrations, and we want to have adequate speed of response, and we want it to be stable. This hood has adequate flow, it's stable, and it has the correct speed of response. If I go over here and I look, I'm starting to question the minimum flow, and it's got some variations, and then the biggest issue is response time and stability. It's overshooting, undershooting. It's got an unstable response. That causes problems not only for the hood, but also for the laboratory, right? From a hood standpoint, there's potential for loss of or escape, loss of containment. From a laboratory standpoint, the flow is driving the supply. So it's also going to be modulating in an unstable scenario. So when we have stable flow, the controller's set up properly, we get good flow patterns through the hood, and we get good containment. But when the flow is unstable, it's fluctuating and it's causing momentary escape from the hood, and that could expose the operator and then cause some adverse health effects. So we want to make sure that the controls are stable and that they have the right speed of response, and the sash movement effect test tells us that information. It's also important to recognize that when the sash is opening, when we're moving the sash from sash open to closed, that the flow that's going through this hood is being regulated by the control valve. And if that valve is hunting and seeking, if it's fluctuating, going up and down, that's the signal that's going over through the controller to modulate the supply. So if the exhaust flow is fluctuating, then the supply flow is going to fluctuate, and then we're going to get an imbalance in the room. And that's going to impact containment capabilities of the hood, secondary containment of the lab, pressurization between the lab and other spaces, and that cascade can create all kinds of dynamics for the space. So we want to make sure that the hood is properly tuned and it's stable, and that the lab is properly tuned and stable to track that hood as it goes up and down. If that's not true, it's going to cause problems with pressurization and problems with the other issues of safety and containment within the space. So I hope that's clear. The air balance from sash open to sash closed, very critical, and it has to, in the case of a negatively pressurized lab, the exhaust should exceed the supply at both sash open and closed, and that offset volume should be constant so that you're getting the same pressurization regardless of sash position. And that allows you to tell whether you've got the proper operation by measuring the sash movement and our room pressurization. We know whether the room is in balance during commissioning and subsequently ongoing during routine tests. So that should always be part of the routine test to do the differential pressure. So accuracy and precision is very important. If you are shooting at a target, whether it's darts or arrows or bullets, whatever it might be, we look at accuracy and precision. If you are all over the target, you're not grouped, then you're not accurate nor precise. If you have good grouping, you may be precise, but not necessarily accurate. And if you get good grouping on the bullseye, you're both accurate and precise. And that's what we expect out of the controls in order for the systems to work properly when we're modulating flow. And I can tell you, we test about 3,000 hoods a year. When we are testing these hoods on an annual basis, we see that improper test and maintenance is responsible for degradation in controls. And we're seeing as much as a 30 to 50% degradation within the first 5 years. So VAV systems that are being installed for energy savings, these modern systems, if they're not properly tested and maintained, will not deliver the savings that's expected and can place the space under an unsafe operating scenario. So it's really critical. Can't stress it enough. We're going to be talking about it again and again through this system. The VAV controls introduce new testing requirements because it's critical that for safety and energy efficiency. Now this plot shows the results of a series of tests at a facility. These are all the hoods that we tested. This was the average face velocity on a scatter plot. And basically we said the acceptable limits for 100 feet per minute average face velocity was 90 to 110. So we would expect the controls to be capable of plus or minus 10% accuracy and precision. And so in this case, we see 73% of the hoods fail to meet our acceptance criteria. 73%, right? Now that does not give much confidence to the safety provided by these hoods. And not only that, think of the work orders that are issued after turning in a report like this. Nobody wants to turn in this kind of a report because all of a sudden the hoods are unsafe is the expectation or the perspective, and the work orders have to be immediate. You've got to go out and fix these things immediately. So that means that there's a rescheduling of all activities to accommodate this. And who knows how long they've been out of tolerance. Was it a day, a week, a month, a whole year? So it's very important that we track this information to make sure that they're reliable and they're properly controlled. I go back to the EPA forms because all of this information is going to be provided and be recorded on these forms. Again, you don't have to develop this information new. It's all part of these forms. They're already available. And so we have the recording of the both for vertical sash and horizontal sash openings, the hood monitor readings, and the velocities are all recorded on these flows. And it has a place to put in your operating modes and your VAV response data. The response time, the stability, the ability to modulate and control can all be recorded here. So, okay, that brings us to the end of the lectures for today. And so now we're going to move over to a more live demonstration. So if you'll just bear with us for a few minutes, we're going to go over to the hood and show you a few things on hood operation and some of the test procedures. Okay, thanks for your patience. We have now moved into the lab and we're in front of our fume hood. And we're going to just kind of walk through a little bit of the inspection. And then we're going to show some examples of the tests that are done. So this hood is a modified fume hood, and it's got a vertical rising sash. It's equipped to a variable air volume system. It's got an airfoil sill. It's got a airfoil on the bottom of the sash that we call a vortex displacement sash handle. As I raise the sash, the VAV system is increasing the flow. Inside the hood, we have a baffle in the back of the hood that's controlling the airflow distribution. So one of the things that we'd want to start with here is a measurement of our opening width. So we would measure the opening width, and it's 63 inches across. And we're going to measure the opening height. Now, sometimes people measure it from the airfoil, and that's wrong. We want to measure it from the work surface to the bottom edge of the sash, and it's 28 inches, okay? So that's the opening height. Now, if we had a restricted vertical sash height, it might be at a lower, say 18-inch opening, right? And we move it down to 18 inches. And that tells us our opening configuration. Now, in this opening configuration, we're going to run through a series of tests. We want to make sure that the side access panels are installed, that the baffles are properly installed, everything is working, the sash goes from closed to open. And so this hood is properly installed and ready to be tested. Let's look at a little bit of what happens on the airflow patterns. We'll move the sash down. So we've got a fog generator here. We can start it and get some airflow coming out. And we're going to look to see what are the airflow patterns inside the hood, making sure that it's on. We're going to look at the vortex inside the hood and how it flows. And as we pull the sash down, you can see that those vortexes move right with the sash. And when we open it back up, it travels up with the sash as well. So it's important to think about the airflow patterns inside the hood and the impact of the sash movement on those airflow patterns. And so this hood seems to be modulating properly, but we haven't gone through the face velocity or the cross draft test at this point, or the VAV response test. So we have some other things to do first, but essentially we know that the hood is modulating flow, it's properly installed, and it's ready to be tested. Okay? So now at this point, we would stop and we would move to the lab environment test and measure some flows. So that's what we're going to do next, is show you how to measure some flows in the duct to make sure that we've got adequate exhaust flow to confirm our face velocity and flow measurements. Okay, Carrie, if you'll go ahead and execute on our flow measurements.
In this video, we will be demonstrating the most accurate method for measuring flow through a round duct by performing a pitot traverse. Verifying proper airflow is useful for a number of reasons, including identifying incorrect flow which could result in safety issues, increased energy use, and inconsistent temperature control, confirming measured flows against flow sensing devices such as those used in a building automation system. Before beginning a pitot traverse, be sure to adhere to your organization's safety policies, including wearing proper PPE and following ladder safety requirements if using a ladder. For the purposes of this demonstration, we will be using an electronic micromanometer by Shortridge, specifically the ADM 870C. In addition to the micromanometer, you will need the following tools and supplies: tape measure, permanent marker, drill with 3/8 inch bit, 3/8 inch duct plugs or duct tape. Also, a ladder may or may not be necessary depending on the location of the duct. The next step is to determine where to take your measurements. It is best to measure at least 7.5 duct diameters downstream and at least 3 duct diameters upstream of any turns or obstructions such as a flow valve or transition. In real-world scenarios, this isn't always possible. Although not as accurate, it is possible to traverse as little as 2 duct diameters downstream and 1 duct diameter upstream from turns or obstructions. Measure your duct size and mark the locations for drilling holes for the pitot tube. The preferred method is to drill 3 holes in the duct at 60-degree angles from each other. However, in this video, we will be using an alternate method which uses 2 holes at 90 degrees from each other. Once the locations for the holes have been marked, use the drill and a 3/8 inch bit to drill holes into the duct. Before traversing the duct, you must mark up the pitot tube with the required measuring points. The number of measuring points is determined by the duct diameter. The duct is divided into concentric circles, each containing equal area. An equal number of readings is taken from each circular area in order to obtain the best average. 3-inch to 10-inch diameter ducts require 6 measurement points, and 10-inch or larger diameter ducts require 10 measurement points. The duct diameter is the inside dimension and does not include external or internal insulation materials. If necessary, clean previous markings from the pitot tube and use a tape measure to mark up the measurement points. Using the pitot tube traverse worksheet for a large round duct, we can determine the measurement points for our 14-inch duct. After marking up the pitot tube, we may begin traversing the duct. Insert the pitot tube into the first hole with the tube located at a 90-degree angle to the duct. The pointed end of the pitot tube must be positioned directly into the flow of air and not at an angle. Using the micromanometer, take one reading for each of the 10 locations. After the 10th traverse measurement, remove the tube from the first hole and insert it into the second hole, again at a 90-degree angle to the duct. Be sure to maintain the 90-degree angle throughout each of the measurement points. Once the final measurement has been taken, calculate the average velocity. The average velocity is then multiplied by the duct area to get the flow rate measured in cubic feet per minute, or CFM. As a last step, insert duct plugs into the holes that were drilled or cover them with duct tape. You should now be familiar with the steps necessary for measuring flow through a round duct by performing a pitot traverse.
All right, so we had a little demonstration there of how to measure the exhaust flow in the duct, but now we want to check the lab environment. And are we under the right pressurization? Okay, so we have another little demo here for you of looking at negatively pressurized versus positively pressurized. Carrie, take us away, please. Okay, welcome back. So now we demonstrated that based on the desired room pressurization, if it's under negative, you're going to see flow coming into the space. Under positive, you're going to see flow going out. Having a little bit of a smoke source and your pressure meter, you can take those measurements and then verify the direction with your smoke. So that's a very important tool. We had a question come in about taking measurements. If you are not equipped with a flow testing system like this, where that it collects the data and uses software to pull it in, you can use another meter like this that has the capability of hooking it up and downloading the data into a computer using the manufacturer's software as well. Now, again, when you're making these measurements, you do not want to handhold these probes in the opening. You want to mount them on a stand or on a ring stand so that you're getting the right position and keeping it stable during the method. So again, you can download this data, use the software included in the meter itself to collect the data, download it, and that way you'll have that readings over time. Now, another element to this, again, showing the smoke test. We expect that when the sash is closed, that we're getting good containment. And when we open the sash, the flow is increasing for the airflow patterns, right? Well, let's look at and do a little challenge to make sure that the hood's functioning properly. And we'll show you the difference between the sash open and closed. And this hood will be challenged across a range of flows. Okay, Carrie, if you'll take us away on that demo. Here we're going to determine the effect of minimum flow on hood performance. We have the hood operating at a minimum flow of 250 CFM, which is approximately 375 air changes per hour. When the sash is in the closed position. When the sash is in the open position, we're operating at approximately 100 feet per minute And so the flow will vary with position of the sash, going to 250 at minimum. Let's close the sash. In the sash closed position, we begin to see the vortex developing within the hood, rolling the airflow down to the bottom edge of the sash with accumulation inside of the hood due to the reduced flow. After waiting for approximately 30 seconds, the hood now appears to be full of smoke. We can raise the sash at 1.5 feet per second. We see a slight momentary reverse flow out of the hood, quickly recaptured, and we're now going to observe the concentrations in the top interior of the hood as they begin to dilute and be removed from the hood. At this flow rate, equivalent to 100 feet per minute through this opening of 28 inches by 63 inches, we now have clearance from the top of the hood in approximately 30 seconds. All right, thank you, Carrie. So the last little video I want to show you before we take some questions and convert back over to the podium here is when the flow is too low. You can see that when that sash is in a closed position, the flow decreases. There's a longer residence time, and we're going to talk more detail about the smoke visualization and the tracer test tomorrow during the second session. But one video I want to show you is when it's too low, it can really create problems. And this last one is called acid rain. And what was happening is that inside the hood, there was a process going on generating acid vapor mist. And when they closed the sash, the flow was too low and accumulated in the duct. So I'm hoping that the sound will tell you a little bit about what's going on inside the duct, because they'll hear a gurgling sound, and that's the accumulation of the acid vapors in the ductwork and in the controls. So Carrie, if you'll run that video for us. So what you heard there was that these acid vapors had accumulated in that duct, and we call it acid rain because eventually it broke through the seals and began leaking out of the ductwork into the lab space itself. So it's critical that we know what's happening in the hood. How is the hood performing? Is it got the appropriate set points for flow to adequately dilute and remove the materials from the system? Okay, if you'll bear with me for a moment, we'll take a few questions and then we'll wrap up for today and get ready for our session tomorrow. All right, so first question. How do you select the proper method for testing combination sash fume hoods? Do you test like a vertical sash hood or like a horizontal sash hood? All right, so this particular sash design that we're showing here is actually a combination sash. It can be used both in the vertical configuration as well as the horizontal configuration. Now you're going to love this because it should be tested under both configurations. From the vertical configuration, some users are going to like this configuration. It's going to be more conducive to their work, and we need to know it works properly. We need to check out the VAV operation. We need to calibrate the monitors and make sure it all functions properly in the vertical configuration. So we're going to place it at the sash stop height. In this case, happens to be 18 inches. But we're going to measure the velocities and the cross drafts and the tracer gas containment all at this configuration. We're going to do that first. We're going to test it on the left, center, and the right. But because this hood has the option of a different configuration of sashes, we're going to test it also as a horizontal sash hood. So in the horizontal positions, this happens to be configured for the right opening, but we want to do the left opening, the center opening, and the right side opening. We're going to talk more about this tomorrow, but essentially, the more opening configurations, the more permutations and combinations of sash configurations means more tests, because we don't want to operate that hood in an unsafe circumstance where the user is operating it because he can, and it be unsafe, and we have a potential for exposure where we could have tested it in advance. Again, I'll go back to the issue of installation. The hood is going to cost somewhere as much as $25,000 to $50,000 to get installed and set up with its controls, the ductwork, the fans, the air supply, the test and balance. And so testing it to verify that it functions properly is only prudent, because the only reason the hood was installed was to protect people. So if we have to do a few extra tests to confirm that it works across a range of operating configurations, that's what's necessary. We gave the flexibility. We should confirm its safety. That's part of the process. Okay, that is lead us to another question here. It says, why test with the sash at full open when the working height is 18 inches? Well, the working height of 18 inches was only, that was an arbitrary height. It wasn't chosen to be the perfect height that's acceptable to all users. You can see in this particular photo that this operator is standing looking through the sash. Now, he was nice enough to put it at the sash opening configuration while I took the picture. But the moment we walked out, he opened the sash up because he couldn't reach his apparatus in the top of the hood. So I want to know, under the worst case scenario, how well does this hood contain? And if it does not contain under the worst case scenario, I should train this operator and say, that's unsafe. It's a misuse of the hood. Be safe, operate at the expected sash opening height. So the test data tells us and gives us data that allows us to then inform the occupants about the proper work practices and the capabilities and limitations of the hood. Now, we wouldn't do it under every case. That's an as manufactured test. As installed, we should already know that's a capability or limitation of the hood. So again, we just use this information to the best, to provide the most safest operating environment that we can and understand the capabilities and limitations. Okay, another question that came up is when you first walk up to a hood, how do you know if it's constant air volume or variable air volume? And I have to tell you that I have no idea how to answer that question because it's very difficult. They're not labeled. A lot of times the hoods, it may look like a variable volume hood. It may have a monitor on there that looks like a variable volume hood, but it may not operate like a variable volume hood. And we don't know if it was designed to operate like a constant volume hood or operate like a variable volume hood. We have to go back to the design information. So it's important that we know this information in advance. Knowing the sequence of information, asking those questions is what's really critical. If it's not available, then you have to look at the components. You may have to get up on a ladder and take a look at the controls. You may have to look at the components that are connected to the hood. It's very challenging to tell between a constant volume and a variable air volume. After you've done a few thousand, you can look at them and pretty much know. But when you're first looking at these hoods, it's very challenging to distinguish the difference. So it's a big issue. Another question is, how is this data collected without the software that we're using? Well, the standard, the standard indicates that you should collect data using a data logger or some mechanism to capture that data at a frequency of 1 hertz or 1 reading per second when you're doing the velocity readings and during the tracer gas containment test. Now, if you don't happen to have the software system that we wrote to facilitate it, a lot of times the manufacturer of the velocity testing equipment has an onboard memory on it. And you can record the data to that memory and then download it later. So that's a way to do it. You can also have a data logger. There's a lot of different data loggers. You plug the instrument in, collect the data, then download it to a spreadsheet. We did that for many, many years. It's a perfectly acceptable way to do it. The important element of it is to gather that data over time so that you understand the variance in flow and or phase velocity and whether it's excessive and potentially causing problems with performance. So I hope that helps a little bit. Okay, there's another question here on testing a floor-mounted hood. So I'm going to step out of here and go to the floor-mounted hood. All right, let's say that you have a floor-mounted hood. All right, This hood is open can be open from the floor, and you might have multiple opening configurations. You could have the top sash open, the bottom sash open, both sashes open simultaneously. Well, the methods are exactly the same. Determine the configuration under which you want to conduct a test. If it has multiple configurations, you have to test them under the different configurations. And that means that if you have the top sash open, you test it there. If you have the bottom sash open, you test it there. Your methods are the same. Face velocity, cross draft, smoke, tracer gas, lab environment, they're all the same methods. It's just how you apply them is different. And for an auxiliary air hood, it's a little bit different still, in that we're going to measure the face velocity, but we also have to measure the downflow of the auxiliary air. And ideally, you would blank off the auxiliary air while you're doing the face velocity. In other words, let it blow out into the room because it's going to impact the face velocity. So a different technique, but the standard and the ANSI 9.5 tells you, it provides guidance on how to do those specific steps. In this class, it's a little more detailed, a little beyond the scope of this class to get into the subtle differences between all of these different hood types. But just remember, set your configuration of the opening and apply your tests in that sequence, and you'll get the information, and then move to a different configuration and repeat again. Okay, so I think that we've covered some of our questions here. Whatever we haven't covered, we'll talk about tomorrow. And so thank you very much for your time. And we'll conclude today's session and be ready for you to see you tomorrow at 1 o'clock p.m. East Coast time.